Let's look at the following exam. This is Math 165. We also call it Calculus 1. This is the first exam from spring 2023. We've got 7 problems to work on. Woohoo! 7! This is going to be a lot of fun. And of course, we should begin, like we do all our tests, by putting our name on it so we make sure we get the credit. Because, you know, we work hard. We should get our credit. All right, well, let's begin. Number 1, part A. A portion of the graph of a function g of x is shown. So we have this function doing a lot of up and downs, it looks like. Find 2 integer values, a, b, so that the average rate of change of g of x over the interval from a to b is 0. All right, what are we testing on here? What is it they're trying to get us to understand? Well, what they're after is saying, do we know what average rate of change is? Now, there's a couple ways to think about it, but one nice way to think about average rate of change is that it's a slope. And in particular, whoops, there we go, slope. And in particular, it's the slope between the point A, g of A, and B, g of B. That is to say, you take g of B minus g of A over B minus A. All right, now what do we want? Well, we want a slope to be 0. Now, when does a line have a slope of 0? Well, when it's flat, right? It's not going up or down, it's flat. So we say, okay, so what we're looking for is some place where we have a flat. Now, there's lots of places that we could draw this, right? Just pretty much draw any flat line you want, and you're good to go. So, for example, between those 2 points, we have a slope of 0, so that's an average rate of change of 0. But remember, it specified the phrase integer. So we're looking for integers. Now, they very kindly marked these points here, so let's highlight them again. So what we can think of is we're looking for a pair of these points which have the same height, so that it's flat in between. And doesn't have to stare too long to see, aha, if we go from 3 up to 6. And so we could say average rate of change from A equals 3 to B equals 6. And there we go. All right, well, that was fun. Part B. Find the average rate of change of f of x, which is 3 over 2 minus x, between x equals 1 and x equals 1 plus h. Simplify as much as possible. So it's a little bit different. In fact, part A and part B aren't related to each other beyond the fact that it involves average rate of change. In particular, this graph is not the graph of 3 divided by 2 minus x. If it were, there'd be some weird asymptote happening at 2, which is not happening. So what is going on here? Well, I just want to make sure we know the definition. And this is highlighting the definition actually of derivative. So you say, okay, what should our average rate of change look like? Well, if we apply the formula, it should look like the following. We should have f of 1 plus h subtract f of 1 divide by 1 plus h subtract 1. Now, where are these coming from? So the 1 and the 1 plus h are acting as our b and our a. Now, it doesn't matter whether you put 1 here and 1 plus h there or vice versa, because in the end, if you do it both top and bottom, it's a sign change, and 2 signs change, they'll cancel out, and life is good. Now, we're not done, but this is in some sense the hard part. We figured out how to get going. And oftentimes in life and math, it's the how do you get started? That's the hard part. Okay, so how do we finish? Well, now it's algebra. And generally speaking, with these kinds of algebra problems, there's only a few techniques you need to know. There's things like how do you get rid of square roots, which is multiplying by conjugates. How do you expand out, factor, FOIL, and how do you work with adding fractions? Now, when we write down what happens here, this becomes the first part, 3 over 2 minus 1 plus h. And I should say, this is another place where people often make mistakes. How do you plug in 1 plus h? And the answer is, wherever you see an x, you put a 1 plus h. And so just remember that. It's not like you add an h on the end of the whole expression. No, it's just whatever you plug in here, that's where the x goes. And parentheses are your friend. Friend. We like parentheses because they help us not lose points. Okay, subtract. Then we're going to have 3 over 2 minus 1. And downstairs, 1 plus h subtract 1 would be h. And so let's write that just to help us follow along as a 1 over h. All right. Well, let's clean that up a little bit. So that would be 3. Okay, the minus distributes, and that's why we want those parentheses. So that would be 1 minus h. And then here, 2 minus 1 is 1. So we have minus 3 and 1 over h. All right, now we're not done. And how do we know we're not done? Well, because it gave us an instruction. Simplify as much as possible, but no more. Now, could we do more? Well, yeah, we could combine these terms. So we would combine them by getting a common denominator of 1 minus h. So that would be 3 over 1 minus h, subtract 3 times 1 minus h over 1 minus h. And all that times 1 over h. Now, let's see what happens. Of course, we distribute here. And so we'll have 3 subtract 3, right? Because there's minus 3. 3 subtract 3 is 0. Nice. Then we have a minus h. So the top becomes h. Downstairs, well, what do we have? Well, we have 1 minus h and 1 minus h common denominator. 1 minus h. And then times by 1 over h. Don't forget that. And now what do we see? Aha, h's cancel. And we should expect it. As long as we've lived a good, clean algebra life, we should expect cancellation like this. And we end up with 1 over 1 minus h. And we're done. We're done. Now you might wonder, is there a way to check this? Well, there's kind of a little bit of a check. It's not a perfect check, but you can say, well, you know, this looks a lot like a derivative, and suppose I were to set h to 0, I'd have the derivative. So this seems to say that the derivative should be 1. All right, well, let's take the derivative and plug in 1. What happens? Well, the derivative here, well, we'd have 3, then 2 minus x to the minus 1 power. So when we take the derivative, the minus 1 comes down, 2 minus x to the minus 2, and then we're going to multiply by minus 1, and, well, plug in 1, and we end up with 3. And like, aha, Steve, error. Yes. So let's fix our error. Okay, so what did we forget? Classic error. See, the 3 multiplies with the h. So it's not h, it's 3h. So this should be a 3. All right, good. It's nice to check, right? Because small mistakes can happen. Absolutely. Absolutely. No matter how long you've been doing math, you'll still make small mistakes. The question is, can you catch your mistakes? And if you can, life is good. Life is wonderful. All right. Good. And now we're done. On to the next problem. Number 2. Evaluate the limit as theta goes to 0, sine of 2 theta over theta. Now this is a classic limit. And so what are we going to do? Well, we're not going to pull out the very powerful machinery, because we don't have it yet, of L'Hôpital. Now, what are we going to do? Well, we're going to think back and say, okay, have we seen a limit like this before? And we actually have. There's this beautiful fact, and let's write it down. so we have it for reference, namely the limit as theta goes to, well, let's not use theta. Let me rewrite it in the more mathematically interesting way. Limit as blah goes to 0 of sine of blah over blah. All right, what is that? 1. Okay, good. So the key here is if you have sine of something over the same something, so your blahs have to match up. I know you're feeling this is very blasé, but you just go with it. So as long as the inside matches with what's underneath, and it's going to 0, then this goes to 1. Okay, so how do we use that? Well, we say, well, sine of 2 theta over theta, what can we do? Well, we can say this is sine of 2 theta over theta, and of course we'll write the limit down. And we say, well, I want to have what's inside match with what's downstairs, because I want these to match. And so what can we do? Well, one thing we can do is we can just add a 2 here. You say, aha, kapla, which of course we all know is Klingon for success. But wait, that changes the problem. Well, no problem. We'll just do another change where these two have the effect of canceling each other. Now in this case, they divide, and it's like multiplying by 1. And you can multiply by 1 as much as you want. Now, we say, okay, well, how does this help us? Well, we have our sine of blah over blah. And we know theta goes to 0, so 2 theta goes to 0. So this part goes to 1. And so that's going to 1. Then we have a 2. So our answer is 1 times 2, which is 2. Now, there's another way to do this problem. And of course, it still relies on this same fact. This fact is a really useful fact. It essentially is what allows us to do the calculus of trigonometric functions. So what's the other way? Well, use things that we know. Sine of 2 theta. What's another way to write sine of 2 theta? Well, namely as 2 sine theta cosine theta. That's the double angle formula. And we'll divide it by theta. Now we'll think of this as 3 pieces. There's the 2, the sine theta over theta, and the cosine theta. What happens to the 2? Well, not a lot. It's 2. What happens to sine theta over theta? Well, sine blah over blah, it's 1 in the limit. What happens to cosine theta? Well, cosine is a continuous function, meaning no surprises. So when you plug in the limit as theta goes to 0, it's like, well, what happens at 0? And the answer is it's cosine of 0, which is 1. And so we get 2. So both of these ideas work. So both alternative ways to get to our answer. All right, now for part B. They like multi-part problems on this test, don't they? That's all right. That just means there's more for us to love. Find the horizontal asymptotes of the function f of x is 2 plus e to the x over e to the x minus 5, and use limits to support your answer. Now you'll notice here it puts an s in parenthesis, meaning maybe there's 1 or maybe there's 2. Well, how could there be 2? And the answer is there's 2 kinds of infinity. Now you can go off in one direction, say we go off this way, that's heading towards our positive infinity, or we can go off in that direction, then we're heading towards our negative infinity. They don't have to have the same behavior, and so we should look at them individually. And horizontal asymptotes are saying what happens when the inputs get large, whereas vertical asymptotes are saying when does the output get large. So we'll start by saying, all right, find the limit. Let's start, we'll be optimist, positives. Positive infinity of 2 plus e to the x over e to the x minus 5. Now what happens is this gets big and that gets big. So it's huge over huge. So what do? Well, again, we don't have complicated machinery, but we don't need it. Simple machinery. We just are saying let's slow it down. push on the brakes. And the way we do that is we say, well, let's figure out what's the big part and divide out that growth. Now in our case, the big part is e to the x. So what we can do is we can say, well, let's divide out by e to the x on both the top and the bottom. And if we do that, we'll be slowing down the growth so that instead of blowing up to something huge, it goes to something constant. And that's good. We don't want to overbreak and go and end up with a 0 over 0. That's just as bad as infinity over infinity. It's just applying the right amount of braking is the key. And if you have to pick, break on the bottom. All right, so, but in our case, they're both e to the x, so we're fine. So upstairs where we have 2 over e to the x. We'll write that as 2 e to the minus x. And e to the x over e to the x is plus 1. And then downstairs, e to the x over e to the x is 1. And then minus 5e to the minus x. And now, this piece, e to the minus x, as x gets large, that gets small. And so, we see that the limit is going to be 0 for that part and for that part. So what's left? 1 over 1, also known as 1. Okay, so that's one of our horizontal asymptotes. All right, well now let's do another one. Okay, good. Well, what's our other one? Instead of positive infinity, we can go to negative infinity. So we have 2 plus e to the x over e to the x minus 5. Now, when we were going to positive infinity, e to the x was getting huge. There's this asymptotic growth. But as we go to negative infinity, what happens to e to the x? It gets small, goes to 0. So this e to the x is going to 0, this e to the x is going to 0. So what do we have? Well, it's actually, you just say plug it in, right? Whatever it means to plug in, negative infinity. We get 2 over negative 5, or we can write as negative 2/5. And so we do, in fact, have two different horizontal asymptotes, depending on whether you could go to positive or negative infinity. So we could just combine them together, because they're horizontal asymptotes are the form y equals something, y equals 1, and y equals minus 2 over 5. And we're done. That's it. Good. All right, another problem finished. On to the next one. Number 3. The graph of a function f of x on the interval between -4 and +4 is shown below. Use this graph to answer the following questions. All right, so part A. The limit as x approaches 2 from below. Okay, so here's 2, and we're coming from below. That means, see that minus? From the negative direction, or from the left. So we're approaching 2 from this direction. And we're saying, well, what's the limit as x approaches 2 of f of x? In other words, as we come in from the left-hand side, what do we think it should be? Well, so we follow the function. We say, well, we think it should be 3, right? Because it's heading towards that point. So we have 3. Limit as x approaches 2 from above of f of x. Now, see above, that's the plus sign, from the positive direction or from the right. So now we're coming in from the right-hand side, and as we approach 2, the function is approaching -3. All right, well, that's not so bad. It's essentially, these kinds of questions are, what do you think should happen? Because after all, that's what limits are about. What should happen? And, well, now we have parts C and D. Circle the bullet that best completes the sentence. At x equals 2, the function f of x, ... all right, is continuous, because f of 2 equals the limit as x approaches 2 of f of x. Now, that's not going to work. Do you see how these two don't match? Well, that means the limit doesn't exist. Okay, so there can't even be a limit. It has a removable discontinuity because the limit as x approaches 2 of f of x exists, but does not equal f of 2. Well, no, limit doesn't even exist. Has a jump discontinuity because the limit as x approaches 2 from below is not the same as the limit as x approaches 2 from above. Well, that's true. See how when we draw, you have to lift up your pen and continue. So that is a jump discontinuity. Has a vertical asymptote? Well, no, because it's not blowing up. So that's not a possibility. And none of the previous 4 choices correctly completes the sentence. No, we found one. All right, so that's part C. Then part D. Okay. Circle the bullet that best completes the sentence. At x equals 2, the function f of x squared. All right, well, let's think about that. Let's think about what's happening. So if we come here, when we take f of x squared, what's happening? Well, f of x squared from the left would be what? So x approaches 2 from below. We're heading towards 3 squared, which is 9. X approaches 2 from above. We're approaching negative 3 squared, which is 9. But what's the function going to do? See, the function at 2, we haven't talked about that yet. That's this filled circle right here. So the function at 2 is 2. 2 squared is 4. So f of 2 squared is 4. So now notice that the left and right agree, but don't match up with the function. Okay, so now let's take a look. Is continuous because f of 2 squared is the limit? Well, no. 4 does not match with 9. Has a removable discontinuity because the limit of the square exists. It does, but does not equal f of 2 squared, which is true. Okay, so that's good to go. Has a jump discontinuity? Well, no, these match, so we're fine. Has a vertical asymptote? No, these aren't blowing up. They're 3 squared, 9. And then none of the previous, no, is that option. All right, so there we go. That's our option. And of course, we make sure we follow the instructions. Circle the bullet. They're very particular about having people follow instructions. You know, and as I say, 4 out of 5 dentists recommend following the instructions on your calculus exam. All right, well, that one was nice. It was actually kind of fun because you didn't have to write down a lot. And this is just testing us on our knowledge. Cool. Well, let's see what the next problem has. Number 4. Use the limit definition of derivative to find the derivative f prime of x for the function f of x equals x squared minus 5x plus 3. Note, you must use the limit definition. Solutions using other methods will not receive credit. Ooh, all right. Well, that's all right. We'll just go ahead and do the limit definition, no problem. So that says, do we remember the limit definition? It kind of came up in an earlier problem with that average rate of change problem. So it won't seem too strange, but let's go ahead and write it down again. So it's the limit. Now, I should say there's 2 limit definitions, but there's one I always recommend. And it's the one where you have h goes to 0. And the reason why I recommend this definition is because it's the easiest to see how to get cancellation. Because ultimately what's happening is you have this expression f of x plus h minus f of x over h. Upstairs, it looks like 0. Downstairs, it looks like 0. You say, more work. Yeah, you know it. But what do we need to do? Well, what we need to do is to somehow cancel the zeros. Well, we know the only thing you can cancel downstairs is an h. So all the work comes into saying, all right, make the upstairs have an h that you can cancel with. All right, so we begin. Now, one thing is be careful with your notation. In other words, always include a limit because they're very particular about things like this. So you want to make sure you follow instructions. Give yourself all the points. Don't let them have any excuses. All right, and parentheses, remember, are friends. So don't forget those. So I'm going to put a parenthesis and say f of x plus h. What that means is everywhere we see an x, there's two of them, we're going to replace it with x plus h. So x plus h quantity squared minus 5x plus h plus 3. Subtract f of x. Now, again, parenthesis. And I want the parenthesis here because I want to make sure I distribute the minus correctly. X squared minus 5x plus 3. All over h. All right, so now's our chance for some algebra. Ah, wonderful. Who doesn't love a good dose of algebra? And really, calculus is just algebra with a few extra steps. So we have, this is the limit. Give ourselves space here because we're going to write down a little bit here. H goes to 0. So x plus h squared would be x squared plus 2xh plus h squared. So that's the first part. Distribute the minus 5 through. Minus 5x minus 5h and plus 3. Subtract x squared minus 5x plus 3 all over h. And now we say, well, we should start hoping for cancellation because that's what happens with these expressions is cancellation. And if you're not getting cancellation, mistakes have been made. So go back and look for those mistakes. So here we see there's an x squared, subtract an x squared, that'll cancel. There's a minus 5x and we're going to subtract a minus 5x, so that will cancel. There's a plus 3 and we're going to subtract a plus 3, so those will cancel. So lots of cancellation expected. And if you're not getting it, go back and check your work. You know, it's one of these great problems where, hey, we want you to succeed. We'll give you things to look for. Now, what's left? Well, there's 3 pieces left that haven't canceled. What do you notice is common to all of them? H. Coincidence? I don't think so. In fact, it shouldn't be, because we know our mindset is cancel h's. Cancel the 0 over 0. So we know we should get some h to pull out. So there's h, there's a 2x plus h minus 5 over h. We say, aha, beautiful. The h's are going to cancel. Life is good. And now what do we have? Well, now we have the limit as h goes to 0 of 2x plus h minus 5. And we say, well, now there's no problem. There's not something downstairs. We avoided our dreaded divide by 0. You know, that's one of the things we're like, divide by 0, no! But we've taken care of that. So we're okay. Plug in h equals 0. And we're left with 2x minus 5. All right, now, there is a check to see if we've got the right answer. Because it says you have to use the limit definition to do the work, but you don't have to use the limit definition to check your work. And as the great mathematicians often say, you should check yourself before you wreck yourself. So what's the check? We have this function, x squared minus 5x plus 3. Take the derivative. Not this derivative, not this way. Just take the derivative like you would, like a normal sane person would. Well, derivative of x squared is 2x, derivative of minus 5x is minus 5, derivative of plus 3 is 0. So you end up with 2x minus 5, which is what we see down here. So that's a great sign. Very, very good sign. All right, good. What a nice, fun problem. And I'll tell you, there's a couple things that you just always know are going to be on a Calc 1 test. This is one that you always know is going to be there. And it's just so easy to anticipate. You know your definitions, you plug in your x plus h's, you expand looking for a way to cancel an h, and then you're pretty much home free. Now, here it happened to be you were doing some expansion, foiling. You might, as I mentioned before, be working on adding fractions. You might be dealing with square roots. But that's pretty much it. There's not that many surprises. So I want you to do well on this problem, on all the problems. You know, just do well. Get through this. This is not meant to hold you back. We're here to help you jump even higher. But anyways, we should go on to our next problem. Number 5. A particle at rest is dropped from a height of 10 feet above ground on an alien planet at time t equals 0 seconds. And it hits the ground after 1/2 a second. So, okay, so, all right, it doesn't take very long to drop 10 feet. While in motion, the position y above the ground of the particle at time t is given by an equation in the form y equals 10 plus a times t plus 10 times e times 1 minus e to the minus 2t, where a is a constant. All right, part A. Find the value of the constant a to complete the equation for the particle's position. Now, what do we know about this particle? Well, we know 2 things. We know what happens at time t equals 0. That's at 10 feet. And for some reason, the aliens have decided to go with the classic English system for measurement. But that's all right, you know. Can't blame them. And then, at time 1/2, we know something. Now, it just says it hits the ground. But what does that tell us? When are we at the ground? Well, we think of the ground as being 0 feet. So we say, oh, okay. So what we know is that at t equals 0, y should be 10. And if you plug that in, you'll notice a times 0 is 0. E to the 0 is 1. 1 subtract 1 is 0. So yeah, that checks out. Everything's good to go. And we know at time t equals 1/2, y equals 0. Well, now it's not quite there, so let's plug that in. So we have that 0 is equal to 10 plus 1/2 a, because we're plugging in t equals 1/2, and then plus 10 times e times 1 subtract e. Right? Sorry, 1 subtract e to the minus 1. E to the minus 2 times 1/2 is minus 1. Okay, well, we can multiply that through. So this becomes 10 plus 1/2 a. And then we have what? We have 10e times 1 is 10e. 10e times e to the minus 1 is minus 10. Ooh, well, that's very convenient. It's like they wanted something to simplify. They're nice. You know, contrary to popular belief, calculus teachers are really nice people. So, okay, the 10s cancel out, and then we say, all right, well, we're most of the way there. We can now just rearrange things. We could, for instance, move the 10e across, and we get that 1/2 a is minus 10 times e, and then multiply by 2, and then that says a should be negative 20 times e. All right, well, there you go. There you go. All right, so now that was our goal, right? Find the value of a. Well, the only value of a that's consistent with having that at time t equals 1/2, where we hit the ground, would be a is negative 20e. Okay, now part B. Oh my goodness, another multi-part problem. They really love us. Oh, you know, some people only get 1 part. Some people, but we get 2. How lucky. Okay, part B. Find the acceleration of the particle when it hits the ground. Include units with your answer. Now, when it comes to units, what do we look for? Well, we need a sort of a distance and a time. And we look for, well, what kind of distance are we using? And we see the word feet. What kind of time are we using? We see the word second. So we're going to have feet per second per second. Or usually we say feet per second squared. It sounds weird because what's a square second look like? But okay, so how do you find acceleration? Well, if you have y is position, then the derivative of y is how position is changing. That's velocity. And the second derivative of y is how your velocity is changing. We call that acceleration. All right, so we're really after y double prime. All right, so let's write down what y is. We'll remind ourselves. So y is 10. And then we have this a. So you can't see it here, so I'll pull it down. So 10, and then minus 20e times t. Now this is e times t, not e to the t. That's going to be important. And let's go ahead and multiply this through. So we're going to have a plus a 10 times e, and then subtract 10 times e times e to the minus 2t. All right, so that's our function. Okay, good, good. Now, what happens? Well, we want to plug in the second derivative, so we got to take the first derivative, right? So y prime. Okay, derivative of 10, 0. Derivative of 20e times t. Now, again, this is e times t, not e to the t. Be careful. You know, this is a time when you want to be really careful with things like handwriting. Sometimes we kind of are a little sloppy with our handwriting and like, whoops, uh-oh. We might read this accidentally as e to the t. No, no, no. It's just e times t. So derivative of t is 1. So we have our coefficient minus 20e. 10e is a constant. There's no t anywhere in here. Here, there's a minus 10e, that's a constant. And we have an e to the minus 2t. So take the derivative of e to the minus 2t. The nice thing is exponential functions have nice derivatives. So what happens is the minus 2 comes down. And we're left with minus 2 times minus 10 makes a plus 20e e to the minus 2t. Second derivative of minus 20e, that's a constant, goes away. And again, 20e is a constant, derivative of e to the minus 2t. Okay, minus 2 comes down. That makes a minus 40e e to the minus 2t. Now, that's our acceleration at any time. We want our acceleration at a particular time, when it hits the ground. And we know when it hits the ground. That was given to us in the problem. It hits the ground at the half-second mark. And so we're going to now say, okay, what happens at time equals 1/2? Well, minus 2 times a half is minus 1. E to the minus 1 times e to the 1, these will cancel out. And so we're left with that minus 40. So we have y double prime is negative 40. Okay, I like the sign, and it's a nice number, so that's good. And what are our units? Well, it's our length measurement, feet, over our time measurement, seconds squared. And we got to include units because it told us we have to. And we're not going to lose any points. We got to get them all, right? Got to get them all. So there we go, negative 40 feet per second squared. Done, done. We're doing great, just a few problems left. So let's take a look at the next one. Number 6, find the equation of the tangent line to the function f of x equals 1 over square root of x at the point a equals 25. All right, good. So tangent lines, bread and butter of calculus 1. We should be really comfortable with tangent lines. So not only should we be comfortable with them, but what they represent. And that's what part B is going to get into. So let's just remind ourselves how tangent lines work. So the basic philosophy is tangent lines are what the function looks like nearby. So we're trying to approximate the function. And the way we find these is we say, well, y is equal to the value of the function at our point. Because if we want to approximate the function, we should kind of match the function at the point. And then plus the derivative at that point times x minus a. So that's our tangent line formula. And you're going to see that over and over and over again. It's just one of those ones that you just want to just know. You say, all right, so what do we need? Well, we need to know what happens at the point, and we need to know the dirt of that point, and of course we have to know what the point is. Now, they told us the point a equals 25. Good. What's our function? 1 over square root of x. So our function is 1 over square root of x. Now, let's rewrite that in a calculus-friendly way. And what do I mean by calculus-friendly? Well, I mean that's consistent with the rules. And in particular, instead of writing it as a square root symbol, let's write it as x to a power, because our rules are in terms of x to powers. So we could say, well, this is the same as x to what number? 1/2? Negative a half, right, because it's downstairs. So x to negative 1/2 power. So f prime of x, well, the negative 1/2 comes down. That's the rule, right? When you have x to power, the power comes down. Then x to minus a half minus 1. Minus a half minus 1 would be minus 3/2. Minus 3/2. There we go. All right, now the tempting thing might be like, aha, do we now just plug these pieces into there? Now there's our f of x. Shouldn't we just plug it in? No, because this is f of x. This is f of a. These parts here, these should be numbers. And what's the right number? These are functions. And so we don't plug them in yet. First we need to do evaluation. All right, so let's do some evaluation. So f of 25. Well, we can go back to the algebra. 1 over the square root of 25. And what's that? Well, that's 1/5. Square root of 25 is 5. Now f prime of 25. Well, okay, so this is, we have a negative 1/2. Then we have 1 over, we can say, whoops, how did I put a 2 there? 25. 1 over 25 to the 3/2. Okay, now you might be getting nervous, like, okay, do we really need to take 25 cubed? I mean, that's going to be a big number. It's like 15,625 or something. But no, we don't have to do that. We actually can pull back a little bit and say, okay, well, let's think about it. We got a cube and a square root. Which one should we do first, the cube or the square root? Now, the cube makes things bigger, square root makes things smaller. Now, here's my advice. Do the thing that makes it smaller first, and then do the thing that makes it bigger. So the square root of 25 is 5. So we could say, oh, okay, so this is like minus, there's a half, and square root of 25 is 5, so 1 over 5 cubed. Okay, that's a little bit more palatable. 5 times 5 is 25, times 5 again makes another 125. So there we go. So we get minus a half times 1 over 125, which we can say is minus 1 over 250. Okay, so now we're ready to go. We just put everything together, and what do we have? Well, we have our tangent line looks like y is equal to our function at our point, so that's 1/5. Our derivative at our point, minus 1 over 250, and then times our x minus our point a, which is 25. Now, some people like to expand, which is not wrong. However, in terms of what the tangent line is trying to do, I think this is actually the best way to write it, because it's really capturing what's going on. It's the value of the function plus the derivative times how much you're changing in x. And if you're ever going to do an application, hint part B, then you really want to keep it in this form. So let's talk about part B. All right, part B. Use the answer to part A to estimate the value of 1 over the square root of 25.25. Okay, now we say, well, wait, what? What does that have to do with anything? Well, notice our function is 1 over the square root of x. So this part right here, this is f of 25.25. And now we have our great aha about tangent lines. See, a tangent line is an approximation. So f of x is approximately 1 over 5 minus 1 over 250 times x minus 25. Now, this approximation is only good near our point of tangency. So near x equals 25. Now, the good news is 25.25 is close to 25. So we say, okay, well, great. So that tells us we can now plug in 25.25 into our tangent line. And that'll give us a good approximation to what the function is doing at 25.25. Because we want an approximation. See that word estimate? We're not after an exact value because we can't get one. Even if we had a calculator, it'd just give us an approximate value to like 12 digits or whatever, however many digits fit on the screen. But an approximation, that we can do. So f of 25.25 is approximately, or we can estimate it to be, 1 over 5 minus 1 over 250 times 25.25 minus 25. Namely, we just plugged in 25.25 for x. Now, we could argue that this is correct, but let's see if we can't make it look a little bit nicer. 25.25 subtract 25, this is the same as 0.25 or 1/4. So I say, oh, this looks like 1 over 5, subtract 1 over 250 times 4, that's a nice number, 1,000. And if we were engineers, which some of us are, well, I'm a mathematician, but my wife's an engineer, and I like my wife. So anyways, 1/5, well, that's what? That's 0.2000, because, you know, engineers want 4 digits of approximation. Subtract 1 over 1,000, 0.0001. In fact, these are exactly those. And we end up with 0.1999. So there we go. There's our approximation. Dope! I'm a terrible engineer. 1 over 1,000 is not 0.0001. It is 0.001. So it's not 0.1999. It is 0.199. There we go. There we go. All right. My wife would be so embarrassed if she ever watched these videos. But I'm safe. All right. 0.199. And so there we go. And now if you ever have to say, hey, what is 1 over square root of 25.25? Aha, it is approximately 0.199. Is it exactly 0.199? No, heavens no. But this is actually a pretty decent approximation. And for all intents and purposes, when you're stuck on a desert island, good enough for whatever you might need to be doing there. All right, well, that problem's done. And on to our next problem, our final problem. Our last problem. These go by so quickly. Okay, compute the following derivatives. You do not need to simplify. So what we're going to be working on is our rules. And we really want to dig into our rules and make sure we understand them. Okay, so part A, the derivative of x squared sine of x. And we look at this and say, okay, what rule are they trying to test us on? We have the function x squared times the function sine of x. It's like we have a product of functions. So this is the product rule they're testing us on. So they say, okay, can't fool us on that one. That's a classic. So the product rule says, look, everybody gets a turn. So it's not like, hey, everybody do it all at the same time, where you take the derivative of each thing at the same time. It's like, no, everybody gets a turn. So what does that mean? Well, say, okay, let's say x squared, it's your turn. Say, all right, x squared says, woohoo, my derivative is 2x. So it's like, great. So then that means we're going to write down 2x. And sine of x, it's not your turn. So you stay as sine of x. And then in the next round, we say, okay, now sine of x, it's your turn. Sine of x says, great, my derivative is cosine of x. And x squared says, all right, well, I'm still x squared because it's not my turn. Derivative of sine is cosine. And now we're done because everybody's had their turn. And so there we go. Product rule. We get 2x sine of x plus x squared cosine x. Life is good. Part B will probably be a little bit more challenging. And, well, it's worth more points, so that's a good sign. That's going to be more challenging. So, find the derivative of tangent of square root of x divided by 1 plus e to the 1.5x. Whew! Even just saying it, it sounds more complicated. Now, what rules are going to come into play here? Well, there's a couple. There's the chain rule. Now, where are we seeing chain rule? We actually see it in a couple of places. You see how we have a square root function inside that tangent? That's a function in a function. So that's the chain rule. We even have one downstairs. See that 1.5x? That's inside the exponential function. So that's, again, another chain rule. What else do we see? Well, the other thing we see is a function upstairs, function downstairs. So that makes this a quotient rule. So it's a chain rule and a quotient rule all at the same time. And we're just like, okay, no worries, plenty of time. So what do? Well, we can help ourselves by sort of remembering some basic rules. Maybe let's, for reference, write down the chain rule. So the chain rule, sorry, not the chain rule, the quotient rule. The derivative of f of x over g of x. What does that turn out to be? Well, that is the bottom times the root of the top minus the top times the root of the bottom, all divided by the bottom squared. And one of the things that makes this tricky is that minus sign. In other words, it matters which one is the top and which one is the bottom. And if you forget, you're off by a minus. It's not the worst thing in the world to be off by a minus, but it's not the best thing either. And all right, since we still have some space here, let's go ahead and write down, maybe we'll write up here, the derivative of f of g of x, our chain rule, is take the derivative of the outside, and then here, the inside doesn't change, times by the derivative of the inside. All right, so these are the two rules that we mentioned. In addition, of course, to knowing the derivative of the exponential function, derivative of the tangent function, derivative of the square root function, and now we just go through. And these problems are like onions, in that there's layers. And they're also a little bit like onions in that tears may be involved. But so let's just go through and be careful and make sure we get everything that we need. Okay, so let's follow through. So the outer layer is a quotient rule. So what do we have? Well, we're going to take the bottom, 1 plus e to the 1.5x times the derivative of the top. All right, what's the derivative of the top? Well, now we're into our chain rule. Derivative of tangent is secant squared. Okay, that's the derivative of tangent. You leave the inside alone, but now you have to times by the derivative of the inside. Well, square root of x is a lot like x to the 1/2, because it is x to the 1/2. So that would become 1/2 comes down, x to the minus 1/2. Okay, so we have bottom times the derivative of the top minus the top, tangent, square root of x, times the root of the bottom. Well, now taking the root of the bottom, derivative of 1 is 0. That's nice. Derivative of e to the 1.5x is e to the 1.5x times 1.5. Now where is this coming from? It's the quotient rule. So the outside function is the exponential function, the inside function is 1.5x. So the derivative of the outside is still the exponential function. So that's the nice thing, is whenever you have e to something, the derivative is always e to that something, then you just have to remember to multiply by the derivative of that something. Derivative of 1.5x is 1.5. Okay, so we have the numerator. And some people call it low d high minus high d low. And if that helps you remember, then do it. And if it doesn't help you remember, do something else. And don't forget the bottom squared. Now, what happens next? Well, we go back and say, hey, we don't need to simplify. And we're like, what? That's awesome. Because this is not a test question about simplification. This is a test question about the rules. And in some sense, by not simplifying, it's easier to say, aha, did you see the rules and did you apply them correctly? And now we're done. That was it, our last problem. Woohoo! All right, well, hope you had fun, and I hope that you're going to do well when you take your own test. All right, take care. Bye.